Okay, so let's do another example in terms of calculating the empirical formula for mass percent composition. So in this case, we're going to calculate the empirical formula of a compound containing 43.7% phosphorus and 56.3% oxygen. All this is by mass percent. So step 1, we're going to convert percent to mass, okay, by assuming a 100 gram sample. Now this is an exact number, the 100, so all of our significant figures will be due to our percent by mass composition. So 43.7% phosphorus. If I have a 100 gram sample, that means I have 43.7 grams of phosphorus. 56.3% oxygen. If I have a 100 gram sample, that means I would have 56.3 grams of oxygen. Okay, now the second step would be this. Step 2 is where you're going to convert mass to moles. Okay, so when we look up phosphorus, we know it's 1 mole is going to be, there you are, 30.97 grams for every 1 mole of phosphorus. And for oxygen, it's going to be 16 grams for every 1 mole of oxygen. Now if you use the more significant figures, it'd be 15.9994, but in this case I'm going to the hundredths, and that's why it rounded up. Okay, so some of the periodic tables will have it just to the hundredths. Okay, so 43.7 divided by 30.97, we'll get 1.41 moles of phosphorus, and for the oxygen we get 3.52 moles of oxygen. So for step 3, once we convert it, we're going to divide by the smallest value. Okay, so the smallest value in this case will be the 1 point, just edge this up just a little here, the 1.41. So we're going to divide everything by 1.41, which gives us 1 mole of phosphorus. And divide this by 1.41, and we get 2.50 moles of oxygen. Now in this case, okay, what I have here is this 2.50, so it's not close to 2 and it's not close to 3, it's in the middle, and we need to take a look at our fractions. So I'm going to talk about fractions up here. So if we take a look at fractions, common fractions and their decimal equivalents. when we're trying to get a formula, remember all of our subscripts have to be whole numbers. And if you take this, you would be writing phosphorus 1, oxygen 2.5. Well, that doesn't make any sense because we can't have half of an oxygen. So what we need to do is take a look to see if that's a fraction. Now, if you are close to an integer, then this you could round up. So generally we look at values that are like within, actually plus or minus 0.01. Okay, so you're better off with the hundredths, but we're going to be looking at the tenths to the hundredths place. But this is clearly not roundable in terms of looking at empirical formulas. So if I look at some common fractions, okay, 1/2, the decimal equivalent is 0.5. 1/3, the decimal equivalent is 0.33, etc. 2/3 is 0.67. And rarer, but you may see 1/4, or you may see 3/4. Okay, so if you look at this, then basically I have a fraction here. So 2.5 is equal to 5/2. So how do I get rid of P1, oxygen 2.5? How do I get rid of the half? You can see the denominator is a 2. So we multiply all of our subscripts by 2. Okay, so 2 times 1 is 2. 2 times 2.5 is 5. And that is how we remove our fractions. So what you need to do is make sure you know your very common fractions. And you can see these are deviating much larger than 100th or even a tenth from your whole number. And so you're going to need to multiply it out. And the way you multiply it out, remember, is if 3/4 is the equivalent of 0.75, then to remove my fraction, you're going to multiply this one by 4. Multiply that one by 4 for the 0.25. This is by 2. Multiply these values by 3 to remove your fraction. So the last step, if you have a fraction, is to multiply, if needed, multiply all subscripts, okay, to remove fractions. And that's what we did here. So our final answer for the empirical formula will be P2O5. And that's the lowest, smallest ratio, whole number ratio for this compound. Okay, so now that you know how to do empirical formula, let's move on to molecular formula. So what are the requirements to do molecular formula? Well, when we went back to a previous example, when we discussed the definitions of empirical and molecular formulas, okay, so this is the exact number of atoms of each element. And we found that, let's take a look at something like this. This is my empirical. We found that the number of units, there's a whole number of units between my empirical formula and my molecular formula. So, this is my molecule, this is the empirical formula. To get here, I needed 2 CH units. Okay, so what are the requirements in order to get the molecular formula? So we need, one, the empirical formula. Now, if it's not directly given to you, there will be enough information for you to derive it. And we've just gone through a few examples of how to derive the empirical formula. And the second, this needs to be given, is the given molar mass, the molecular weight. Okay? So, how do we do this? Let's do it with this example first, and then we'll do a second, more elaborate sample. So in this example, okay, the empirical formula we have, CH. So how do we get the molecular formula? Okay, so if our empirical formula is CH, and we know the molar mass, the molecular weight, and that's going to be, say, 26.02 grams per mole. Okay, so the steps we take are: 1, calculate the empirical formula, molecular weight. Okay, and once you do that, 2, you're going to divide your molecular weight, let's say the empirical formula weight. That may be easier to keep track of. The molecular weight by the empirical formula weight. Okay. And this should be a whole number. So if you don't have a whole number, then you're going to need to recheck it. Okay? It should be a whole number, really, really close to a whole number. And really close is just like what we were discussing for empirical formula. And 3, you're going to multiply the subscripts of the empirical formula by your whole number obtained in 2. Okay, so from step 2, you're going to need a whole number. You're going to multiply all your subscripts with it. Okay, so let's do 1. Calculate the empirical formula weight. So carbon is 12.011. Hydrogen is 1.008. So we get 13.019 grams per mole. Okay, so we did 1. That is my formula weight. Now we need to divide the molecular weight by this empirical formula weight. So let's do step 2 now. So the whole number, we're going to call this n, just so we have some variable. So n is going to be equal to the molecular weight, 26.02 grams per mole, divided by the empirical formula weight, the 13.019 grams per mole. And what we get is 1.99862, which basically 1, 2, 3, 4, you round it up, it's going to be equal to 2. Okay, this is within our plus or minus, actually a hundredths. So n is going to be equal to 2. So now that we have our whole number, we're going to multiply the subscripts of the empirical formula by the whole number. So if this is my empirical formula, and n is equal to 2, then you're going to multiply each subscript. So 2 times 1, 2 times 1, and what you're going to get is C2, excuse me, I can't multiply, H2. Okay? So this, and notice it's a molecular formula, so we don't have any parentheses to tell us the groups in there, not typically. Okay, sometimes we do, but in this case, when we get our molecular formula, they're going to multiply everything out and avoid the parentheses. So this is our molecular formula. Okay, so let's do one more example. All right. So with one more example, let's do, we have a compound. So let me just say a compound, so we have a nice sentence. A compound with a molecular weight of, let's say, 42.06 grams per mole. Okay, has a mass percent composition of 14.3% hydrogen and 85.7% carbon. Determine the molecular formula. Okay, so let's go through this. To get the molecular formula, what do you need? We need the molecular weight, and empirical formula. Okay, well, we have the molecular weight, it's right here. So that part's good. But we don't have the empirical formula. So then, to backtrack, before we can do this one, we need to get the empirical formula. And with the empirical formula, you can already have everything in masses, or you can have everything, the composition in mass already, or you can have the composition in percent. So, let's see, do we have percent composition? Oops. Not percent composition, and in fact we do. Okay, here and here. So we're going to have to do the empirical formula first, and then once we have this, we can then do the molecular formula. Alright, so let's do the empirical formula. I'm not going to rewrite the steps, okay, because I think right now with these examples you should have them known. Not have them written down next to you as you're doing these problems. So let's go ahead and get started. Let's do the empirical formula. So step 1 is we're going to assume a 100-gram sample, And if we do that, then all our percent compositions become mass. So we have 14.3 grams hydrogen and 85.7 grams carbon. Now, if we don't assume 100 grams sample, and you say, I want to assume a 1 gram sample, then you would take 14.3% of 1 gram. So you can have any size sample you want, but the nice part about assuming 100 grams is that here we don't even move the decimal point, we just change this percent sign to grams. Step 2, we're going to convert mass to moles. So we know it's 1.008 grams of hydrogen for every 1 mole of hydrogen. We also know it's 12.011 grams of carbon for every 1 mole of carbon. Okay, so let's calculate out our numbers. 14.3 divided by 1.008. I get 14.2 moles hydrogen. And with the carbon, 85.7 divided by 12.011. And I get 7.14 moles of carbon. And then our next step is to divide by the smallest value. So that's 7.14. This is 1 mole carbon. And here, let's see, I get 1.98. So 2 moles hydrogen. Okay, because it was really 1.988. Okay, so we're going to round it up to 2. You can see that we're very, very close within the 0.1. Okay, so now we have our empirical formula. Our empirical formula is C1H2. Now that we have that, now we can move on to step 2. So step 2 that we were talking about is that we had the molar mass, the molecular weight, and an empirical formula. So let's get our molecular formula because that's what we're after. Okay. So with a molecular formula, we need our empirical formula, CH2, and the molecular weight, 42.06 grams per mole. Okay, and what we did is we calculated the empirical formula weight. Okay, and that's going to be equal to 12.011 grams per mole plus 2 times 1.008 grams per mole. So what we get is 14.027 grams per mole. Okay. Now we divide 42.06, the molar mass, divided by the empirical formula weight, the 14.027. So I said we'll just set the whole number variable to n, just because I'm used to using n for my whole numbers. And we know it's going to be the molecular formula weight, 42.06 grams per mole, so it's my molecular weight, divided by the empirical formula weight, and that's 14.027 grams per mole. And what we get, 42.06, you get something like 2.9985, and we want a whole number, and this is going to round up to 3. Okay. Now that we have our whole number, what we have to do is multiply all my subscripts by this value. So let me just go ahead and go through this. So when we multiply CH2, we determine N was 3. Our molecular formula is going to be C3H6. Multiply it out, and this is what you get. And we do that when we talk about molecular compounds, multiply them out. Okay? So that's basically how we did a whole group where you're given the information you have to calculate, determine your empirical formula first before you can get to your molecular formula. So we had to take this into 2 steps, and then each step has multiple parts. So just be aware and map everything out as you go. What do we need? And then try to make sure you have everything you need before you solve that problem. Okay, and that's the end of this chapter.